Hi and a very good day to Dr. Hamdan and everyone. We are from Group 1. Idiako Sunjan Berhad would like to present our design project, production of ethylene from feed of 100 ton per month methanol. Before going further, I would like to introduce myself. I'm Matesha Analaki Gunarayu, matrix number 195980.
My name is Farah Rahana Bidi Shafi'i, matrix number 198.14.
My name is Nur Hanis binti Mamano. My matric number is 198743.
My name is Nazira binti Zulkarnain and my matrix number is 198742.
First of all, the aim of the project of this plant design is to provide a comprehensive overview about olefin, particularly ethylene production with purity of 99.99% and its commercial significance in a global market. This plant design aims to achieve its purity of ethylene through emptier process, which is methanol to olefin.
The first process for this plant design is for the feed, it is methanol with 4.2568 kilomole per hour, which we convert from 100 ton per month methanol that consists of ethanol and water with 0% of DME. So the first feed will go through pump, which is used to increase the pressure of the fresh feed from 1 bar to 16 bar. So the next unit is heater 1, which is used to increase the temperature from 318 Kelvin to 523 Kelvin for the next unit.
Then we go on to reactor. So this is an isothermal reactor that purposely to convert methanol to DME. So as it is isothermal, the temperature maintains the same from inlet to outlet, which is 523.15 Kelvin and 16 bar. The next one is cooler. So cooler will cool the stream from 523.15 Kelvin to 373.15 Kelvin. So that it will reach an optimum temperature before you enter the distillation column. Then for the distillation column, there's two streams, upper streams and bottom stream. So the bottom stream will be 433.83 Kelvin and the upper stream will be 396.57 Kelvin. So the purpose of this distillation column is to increase the purity of DME. And also the bottom stream will be recycled later to the reactor.
Okay, for the heater 2, the aim of heater 2 is to increase the temperature before recycling to reactor 1. The inlet temperature of the stream 8 is 182.68 Kelvin and the pressure is 16 bar. So the temperature is to increase to 523.15 Kelvin. For heater 3, distillate from distillation column is passed to heater 3. The heater 3 increases temperature from 386 Kelvin to 723 Kelvin at 16 bar. For reactor 2, the stream that enters reactor 2, the reactor 2 is assumed isothermal reactor. The purpose of this reactor is to convert DME to light olefins such as ethylene appropriately, and the temperature outlet is the same, which is 723 Kelvin at 16 bar. For cooler 2, the purpose of cooler 2 is to reduce the temperature from 723 Kelvin to 320 Kelvin. The pressure was not affected in this unit since the both input and output pressure is the same, which is 16 bar. The composition of the components are not changing in this unit as well because there is no reaction occurring.
So the next unit is the dryer. So the purpose of this dryer is to remove water components so that the mole composition of ethylene will increase. So in this unit, we assume that 100% of water is being removed from the dryer. This stream consists of the other components in 1.6288 kilomole per hour at 293 Kelvin temperature, and the outlet pressure for both streams are constant at 16 bar.
Next is condenser. This condenser is used to condense the vapor to liquid, which is the optimum phase to de-ethanizer, which is the next unit. So the temperature goes out from the condenser is 204 Kelvin and 16 bar. And there will be no any reaction will take place since it's a minor unit. Next, de-ethanizer. From the condenser, it will enter the de-ethanizer, and this de-ethanizer mainly to separate the light olefins such as ethylene and propylene from the bulk component, as it can help to achieve 99.9% of ethylene at final stream. Unfortunately, we couldn't achieve 99.9% purity of ethylene. So we add another column basically. So how we are the top overhead product, which is ethylene and propylene, because they have the low boiling point and compared to the other bulk components. So it will be at overhead and other component will be bottom, and the bottom will be removed and the overhead will enter to the next unit, which is fractionation. Okay, basically this fractionation to increase the purity of ethylene up to 99.9% and be able to achieve 99.4% purity of ethylene using fractionation at the constant pressure and temperature of 196 Kelvin. So basically this will be our overall balance, where there will be one feed which is 136.99 kilogram per hour, and there will be a 5 outlet with purging, dryer, de-ethanizer, and 2 fractionation. If we sum up all the outlet, we will get 136.91 kilogram per hour, and our inlet is 136.99 kilogram per hour. So when we will minus it, we get 0.08. It should be 0 due to some round off error in calculation. There's some significant error, which is 0.08. So next is our block flow diagram. Since it's too big, we compress it into the presentation slide. It's not clear, sorry for that. Okay, this is our process flow diagram, where you can see from the tank until we achieve our desired product, ethylene with 99.4% purity.
Next, we will proceed to the Aspen comparison. So for the first unit is the pump. As can be seen on the table, the molar and mass flow rate and pressure difference of pump is similar in both calculations. The only significant difference is in the temperature and the net work required. There is no energy loss, but there is work required to convert rotational energy from water to induce flow and raise the pressure of liquid. So even though the work required is less, there is difference between manual calculations, which is 0.071276 kilowatt, and Aspen calculation, which is 0.24826 watt due to small temperature difference. So for the next unit is the heater. So based on the table, it says that the heater is used to increase the temperature of heater 1 from 318.15 Kelvin to 523.15 Kelvin, while heater 2 is from 433.83 Kelvin to 523.15 Kelvin. So the temperature also shows slight difference between manual calculation and Aspen calculations. For heater 1, the temperature difference is only 205 Kelvin in manual, while 403.51 Kelvin difference were calculated in Aspen calculation. This is because to maintain a constant pressure and heating up at the same time, more heat is needed to increase the temperature and cater with the constant pressure. So that is why in Aspen, the temperature is significantly higher than the manual calculation.
Okay, so next for the reactor, there's a significant difference between the mole flow rate and mass flow rate between the manual calculation and Aspen simulation. So in Aspen calculation, it has higher flow rates. This is because we assume in Excel that we have purging, which means the flow rate that comes in the recycle stream is less than the Aspen. So that it explains how why the Aspen mole flow rate and mass flow rate is more than the manual calculation. And then for the temperature, it is the same for both because it is an isothermal reactor, as we assume. Okay. Okay. So for next is for cooler. Same with the reactor. It has differences both in cooler 1 and cooler 2 for mole flow rate and mass flow rate. This is because as explained before, we have purging in Excel compared to Aspen simulation. So that's why it has higher mole and mass flow rate. So for the temperature, it is because it links with the higher flow rates in manual calculation, in Aspen simulation, higher flow rates in Aspen simulation, and resulting in more energy released compared to manual calculation, both with cooler 1 and cooler 2. Next, for the distillation column, the flow rates and mass flow rates like before, it assumes purging in manual calculation rather than Aspen. For the temperature, it has slight difference because we in Aspen simulation we assume and we set the setting as 0.6 bottom to feed ratio. So it has higher flow rates in the bottom stream than upper stream, and that results in lower composition of DME on the upper stream compared to the manual calculation. And also the heat duty and boil up rate also affect the network and also the temperature difference. So for the network, it has more heat released both in vapor and bottom stream, heat absorbed and heat released compared to the manual calculation. And as explained before, this is because we set it as what is it called 0.6 bottom to feed ratio. So it has higher flow rates in lower stream, and it needs more energy to maintain its temperature, its optimum temperature.
So as for the DTO rate, there are some difference between as a manual calculation at Aspen, which are at to the energy rate, and also the Q because the mole affects the number of affects the calculation in Q. So for the pressure is the same and temperature is the same because the reactor is isothermal reactor.
So the next unit is the dryer. As can be seen on the table, the only difference where the mole and mass flow rates, where the Aspen shows higher compared to the manual calculation. So as Farah explained earlier, the difference is because the presence of recycled streams which affect the flow rates. As in Aspen, there is no purging occur compared to the manual calculations. So from the manual calculation, the temperature varies since the product stream calculated using Rod's law, while in the Aspen simulation, it was calculated as flash, where high volatile components discharged in vapor phase, while low volatile components discharged in liquid phase. Since water has a very high boiling point, all the water removed in liquid phase and other components enter to the next unit.
Okay. Next is condenser. There's significant difference in mole flow rate and mass flow rate. It is because, as like my previous group members said, there's a purging occur in manual calculation, but in Aspen simulation there's no purging. So there's a slight difference in mole and mass flow rate. And the temperature difference over here is that you can, as everyone can see, manual calculation is 363 and Aspen is 323. It's because in manual calculation we determine it according to the journal. In Aspen, the Aspen will calculate for us for the outlet part, especially for the reactive part. So there's some difference in temperature. So as the temperature drop is high, the energy release also will be high. So we can see from the manual calculation and the Aspen, the temperature drop is quite low in manual calculation. So the energy release is quite low compared to the Aspen, and it's negative because the heat is released to the surrounding. Next is de-ethanizer. For the de-ethanizer, the mole and mass flow rate is still have a significant difference due to the purging stream. And then the temperature, as I said before, due to the previous unit that for the Aspen, it will calculate for us. So there's a slight difference. Due to the temperature difference, the energy also differ over here. So over stream 17 for manual calculation and stream 18 for Aspen calculation, we can see that there's a negative. It is due to there's a presence of condenser where the heat will be releasing, and at the bottom there's a reboiler, so heat will be absorbed. So there will be a positive for stream 18 for manual and stream 19 for Aspen. And over here, all the components are in liquid phase. Okay, this will be our last unit for the fraction for our manual calculation. Fractionation is last unit for our manual calculation, but for Aspen simulation, there's no fractionation. It is due to because in Aspen simulation for de-ethanizer, we could be able to achieve 99.6% purity of ethylene. It is due to because of the temperature difference and the flow rate difference. But however, for the manual calculation, we not able to achieve that purity using de-ethanizer. We only able to achieve 94% of purity of ethylene only. So that we add a fractionation to increase the purity of the ethylene. So from the fractionation in manual calculation, we get 99.4%, which is same, no, sorry, which is low a bit compared to the Aspen, which is 99.6 in the ethanizer. So Aspen simulation, if we add fractionation, it will be a huge loss because this is a major unit. And from the manual calculation, we're able to calculate the stages for fractionation. It's needed 2.3 stages only because the inlet purity is already too high, which is 94% for fractionation, and the outlet is 99.4. So we need 2.3 stages only. So it's like proven our hypothesis.
Okay, so for the recycle stream was added in order to utilize the waste in useful way. Recycle stream is chosen from distillation column to reactor in order to increase the purity of DME, which is our most desired component in MTO process. This is due to olefin produced from DME, where the DME purity increases, indirectly purity ethylene increases. So it has three stages that we will explain later, which is the recycle stream that we choose, the purging occur, and the mixing, and the final flow rate that will enter the reactor. Okay, so for the recycle stream, we decided to choose the bottom stream of distillation column. This is because the composition of the bottom stream of distillation column is consists of methanol, ethanol, water, and DME. So it acts as the raw materials for the reactor. And before it enters the reactor, it enters the heater so that it will increase the temperature before it enters the reactor inlet. So the composition itself will increase the purity of DME that will occur, and thus increasing the purity of ethylene.
Next, for the purging, since the outlet of the bottom stream of distillation column is 4.5562 kmol per hour, then it will undergo purging with the same flow rate and composition at 2.2781 kmol per hour. So the purge stream is one where a portion of the recycle stream is removed from the system in order to avoid accumulation of undesired material in a recycled stream.
For the mixings, the outlet stream from the heater 2 come in contact with the outlet stream with heater 1 and become a new stream for the inlet for the reactor 1. The more rate increases because the two the two stream were in contact.
Okay, so for the costing, it is for our economic analysis. So for this is the cost of raw materials, methanol with 97% purity, that we decided to buy from China, and this is the price for 2019. And based on 100 ton per month of feed, and this is the results of calculation for maximum cost and minimum cost per year and per 20 years. Okay, next is the cost of maintenance. So it consists of wastewater treatment, via quality alam, and also electric. So these two are is considered to be the maintenance and will be calculated in the maximum profit later. So the wastewater treatment is 6,100 per 20 years, and also the electric will be 8,934,874 ringgit for 20 years. And for the income and profit sales, okay. So our main product is ethylene, and our byproducts are ethane, propylene, and propane. So we take the profit of these four products that we will sell in Southeast Asia and also China, that will give us the maximum income and minimum income of between 51 million to 68 million. So this is the maximum income and minimum income. So with the maximum income, maximum and minimum income, and also the maximum and minimum cost, we get to calculate the maximum profit and the minimum profit. So in the table, as we can see, it have negative 1 million of profit, of maximum profit for 20 years, and also 2 million per 20 years at loss. So the maximum profit and the minimum profit calculated here indicates that in 20 years, our company is still at loss.
Next, we will now proceed to the feasibility of design. So first, in terms of technical feasibility, this design plan is technically feasible. This is because this design only requires 7 main units, which is in its minimum range and use reliable resources when it is being operated. Secondly, in terms of economic feasibility, this design plan does not have its viability and it is not economically feasible as well. This is because based on the economic analysis made to make the cash flow, our company is still operating at loss after 20 years being operated. Thirdly, in terms of sustainable development, the two most widely used components to make plastics are ethylene and propylene, and both have traditionally been derived from crude oil. It also produces the highest yield of light olefins at the lowest cost of production, with the lowest catalyst consumption and the lowest operating costs.
In conclusion, MTO process that our group has chosen consists two stages. First, the methanol converted into DME, which is dimethyl ethyl, and then from DME to olefin, we call that as DTO process. By feeding 100 tons per month on methanol, our company can produce 199.009 tons ethylene per year. From the process, our final product should be ethylene, propylene, and all these products are selling in the market. Support 34, the catalyst that has been used in the reactor, help high conversion of them in the reactor. The purity of ethylene produced is 99.4%. The number of 32 stages in fractionation column is 2.3, including reboiler, and the reflux ratio is 1.979. From the calculation of costing of the maximum income calculated is 68,979 and 632.69 ringgit Malaysia, and the minimum is 51,775.15 for 20 years.
Okay, for the recommendation, we have the first is we have to reduce units to save costs. We have to do more research on the units, and as I said, from the Aspen, we have reduced one unit, the fractionation, which is a major unit. It can lead for us to costing maybe to reduce the major unit. Second is waste treatment should be handled carefully for environmental safety. Since we are using two different reactor, it should be considered. And the third is use a distillation column with high temperature so the purity of ethylene can be achieved, although it might ensure higher maintenance and production costs. And the fourth is reactor with high efficiency should be used in order to produce more DME so that more ethylene can be produced. And the last is insulation required for distillation column separator and fractionation for energy savings and prevent from the column being affected by swing in the weather, changing the heat transfer rate at the tower surface. It is due to there's the existence of the condenser and the reboiler. That's all from us. Thank you.
Thank you.
Thank you.
Thank you.